Welcome to the video lecture on signals and systems. This video we will discuss about analysis of LTI continuous time system using Fourier Transform. So though you have a dedicated unit for discussing about analysis of continuous time system, we still discuss a brief notes of what it is all about. So first of all, we will discuss about the transfer function in this case. So kindly refer to the last equation I put here. Transfer function is equal to y of j omega by x of j omega. So what is this x of j omega? We have already seen this notation in the previous video. This is nothing but Fourier transform of the signal x of t. So let us begin this way. Let x of t be input to the continuous time system and let y of t be the output which you get in response to apply this particular input x of t. So now x of j omega is Fourier transform of x of t and y of j omega is Fourier transform of y of t. So altogether now we define the transfer function as y of j omega by x of j omega. So the ratio of the Fourier transform of output and the Fourier transform of input is called transfer function. So in general, transfer function of an electronic system is nothing but it is a mathematical function which theoretically models the device output for each possible input. So as you can see in the first figure, when you provide an input called x of t to a continuous time system, you get y of t as a response. Now, we have to discuss about an important point called as impulse response. So what is this impulse response? Say suppose you have a continuous time system and that is called as h here. You apply an impulse input at the input side. So whatever output you get when you apply an impulse signal at the input, so this output is called as impulse response. So what is the importance of this impulse response? This impulse response plays a very important role if you wanted to discuss about the output response for any given LTI system. So the output response for any given LTI system is nothing but convolution of the impulse response and the input response. Now this will give you a better figure of what I am talking about. Y of t is equal to x of t in convolution with h of t. So this is what I have been telling you. If you wanted to analyze the output response of a system, then you will have to obtain the convolution of the input signal or the input response with the impulse response. So this convolution operation can be defined as y of t is equal to x of t in convolution with h of t, which is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau, where this tau is nothing but a dummy variable for integration. So now let us assume these variables. H of j omega is nothing but Fourier transform of h of t. X of j omega is nothing but Fourier transform of x of t. Y of j omega is nothing but Fourier transform of y of t. Now from this convolution statement, let us see how do we arrive at the transfer function. Now y of t is equal to x of t convolution with h of t. Take this expression. Let us assume, let us apply Fourier transform for this. And we have an important property of Fourier transform under this, which is nothing but the convolution property. Now the convolution property of Fourier transform states that if you have any signal in convolution, x of t convolved with h of t, and if you apply Fourier transform for this, the Fourier transform of this signal will be multiplication of the respective Fourier transforms. So Fourier transform of x of t convolution with h of t will be x of j omega and h of j omega, which is put in multiplication. So x of j omega into h of j omega. What is x of j omega? Fourier transform of x of t. What is h of j omega? Fourier transform of h of t. So we will equate this equation like this. We will assign a variable called y of j omega. So y of j omega is equal to x of j omega into h of j omega. So from this, what is h of j omega? Cross multiplication. Y of j omega divided by x of j omega. So this is how we arrive at the transfer function in frequency domain. So this transfer function in frequency domain is literally given by Fourier transform of the impulse response. So that is the importance of impulse response. So now look at this. Now this will exactly tell you the relationship between Fourier transform and Laplace transform. So what is Laplace transform? This is another transform which we use for analyzing the continuous time systems, just like Fourier transform. So let's go like this. Let x of t be the continuous time signal defined for all t. So this is the definition for a Laplace transform. A Laplace transform of x of t will yield x of s, which is equal to integral minus infinity to plus infinity x of t e power minus st dt. Now if you look at the Fourier transform definition, this is a Fourier transform definition. Look at the last equation. Fourier transform of x of t will give you x of j omega, which is equal to minus infinity to plus infinity x of t e power minus j omega t. So look at the first expression and the second expression. We have a minute difference between these both. So the equation which connects the first equation and the last equation is the middle equation here. So take the Laplace transform expression. We have e power minus st. So substitute s as sigma plus j omega in the above definition of the Laplace transform. So when you do so, you get it as x of s is equal to integral minus infinity to plus infinity x of t e power minus of sigma plus j omega t dt. So compare these both expressions, the first equation and the second equation. So from this we conclude that the Fourier transform of a continuous time signal is obtained by letting this sigma equal to 0. That is, we substitute s as j omega in the Laplace transform. So since s is equal to sigma plus j omega, we will say that the Laplace transform is a generalized transform and Fourier transform is a particular transform when s is equal to j omega. Since s is equal to j omega represents the points on the imaginary axis in the s-plane, we can say that Fourier transform is an evaluation of the Laplace transform along imaginary axis in the s-plane. Also, since we call Fourier transform to be an evaluation of Laplace transform along imaginary axis, the ROC of x of s will definitely include the imaginary axis. Now when I say ROC, region of convergence, where the particular transform is said to exist. So for all causal signals, the imaginary axis is included in the region of convergence. So therefore, for all causal signals, the Fourier transform is said to exist. So that's all for today's video. In the next video, we will discuss about Fourier transform of some basic signals. Thank you.